All right, we have another motion problem. So again, I'm going to start by taking inventory. An apple falls out of a tree a distance of 5.5 meters. So delta x, we're going to call 5.5. Oops, move that back. So delta x. So you might say, well, if it's falling vertically, shouldn't that be delta y? And sure, you could use delta y, but we're just using delta x for this. It's all linear motion. We don't have to really worry about if it's x or y. Anyway, so that's delta x, that's the distance before hitting the ground. How much time was it in the air? So this seems, at first glance, like they really didn't give us a whole lot of information. I mean, how are we supposed to answer a problem knowing only delta x and nothing else? But what's not said here are there are several things you can sort of imply or infer from the problem that will help you solve it. So if an apple's falling out of a tree, that means initially the apple was in the tree and pretty much motionless. So we can make the assumption that V naught is equal to 0 meters per second. It's not being thrown out of the tree, it's just falling. It was motionless and then it fell out of the tree. So that's one assumption. The other assumption we can make is this is falling because of gravity. So on Earth, gravity, the acceleration is going to be 9.8 meters per second squared. And because it's falling, we're just gonna keep this as a positive number. It'll make things a little easier because it's not changing direction. We don't have to worry too much about that. So anyway, we know A. So now we know some more information. We can look and try to find something to do this. So my first equation, again, is no good. I don't have my average velocity anywhere, so I can't find time. My second one doesn't have time in it, so that's no good. My third equation, let's see, I have time. I don't have time. I'm looking for time. I have acceleration. I have V naught, but I don't have VF, so that's no good. So I'm looking really at the fourth equation here. Delta x equals V naught t plus 1/2 at squared. So delta x, so I'll plug in the numbers, 5.5. And again, just a quick unit check. These are all in meters or meters per second or second squared. These will cancel, so I will, I guess, get rid of the units for this to make it a little easier to see. So delta x, 5.5, equals V naught, 0, times t, plus 1/2 a, which is 9.8, times t squared. And just to make this easier, 0 times t goes away. So I have 5.5 equals 1/2 times 9.8 t squared. It's a lot easier to deal with this if we just combine numbers as much as possible. So 1/2 times 9.8 is really 4.9 t squared. And over here I have 5.5. So I want to solve for t squared, get that by itself. So divide each side by 4.9. I get, okay, t squared equals whatever 5.5 divided by 4.9 is. And that comes out to 1.12. Actually, 122. I won't round until later. And to find t, I'm going to have to take the square root of both sides. So the square root of that answer, I get about 1.06. And it's going to be in seconds. So that is how long this apple was in the air. If I want to confirm this, if I want to confirm I did it right, I can plug this back into this equation. So we'll have 0 times 1.06 plus 1/2 times 9.8 times 1.06 squared. And I'll just double check that. So 1.06 squared times 9.8 times 1/2. And I get 5.5. So it checks out. It looks like I did all right. So that's the final answer of this motion problem. So until next time, I am Derek Genova. Have a delightful day.